Welcome, this is Dr. Plague, and today I'm going to have a little fun messing around with designing another simple CPU, the Plague Mark II. If you're not familiar with the Plague Mark I CPU, you might want to go back and watch those videos since I'll be basically expanding upon that design. And this won't be a very impressive CPU, it's just a little something that we can play around with. And it will execute code out of a flash or ROM memory chip. It'll do some simple math, it'll take user input and have output, and it'll make simple decisions with conditional jumps. Now, just like with the Plague Mark I CPU, I will be designing the Mark II in a few different steps. I'll first build the design in simulation software, then I'll get it working on a breadboard. I'll start out supporting just a few instructions, which will take about 7 logic ICs to create. Then we'll test that out. After that, I'll design a very simple assembler to help with creating the binary, aka hexadecimal machine code. Then we'll write a little code and design a circuit to test it out. After that, I'll add some more instructions and we'll update the assembler and give everything a test. The final version should contain about 12 logic ICs, not very complex, but it will support a total of 8 assembly language instructions, with a possibility of adding more. So now that we have a game plan, let's get started. I'm going to use a flash memory ROM chip to hold the code. This is not part of the CPU, but the CPU will connect up to it. If you'll remember back to my part 1 video on designing the Plague Mark I ended up using the 74161 counter IC as our instruction pointer register. And just like before, we'll connect that up to our flash memory chip, which will hold our CPU instructions. And remember that I don't connect the power and ground pins in the digital simulation software to avoid clutter, but we'll need to remember to do that on the breadboards. Now, before we get any further, let's talk about the format for the Plague Mark II CPU instructions. If you remember back to the Plague Mark I, the CPU instructions contained a 1-bit opcode and sometimes an operand or two. And just like with the Plague Mark I, the Mark II CPU instructions will be 8 bits wide, but the most significant 4 bits, or upper nibble, will contain the opcode this time. So the Plague Mark II opcode will be 4 bits, and the lower 4 bits, or lower nibble, will be reserved for any operands that an instruction may have. So, altogether, we have a 4-bit opcode and a 4-bit operand that makes up the 8-bit instruction. Now, the operand in the lower nibble could contain an address, just like with the Plague Mark I. So, I'll connect the lower nibble to the preset inputs of the counter. We'll make use of those inputs later. So, this is starting to look a lot like the Plague Mark I CPU. But what that CPU did not have was a halt instruction. So, let's create one. This instruction will do exactly what it sounds like it would do. It will halt the execution, or in other words, stop the CPU from executing any more instructions. I'll use the most significant bit of the opcode to do this. We'll set it to 1, and the operand won't matter, so I'll mark it with X's. Now, to get the CPU to halt, we can just stop the counter from counting, and we can use pin 10 to do that. Pin 10 needs to be high in order for the counter to count, so we need to bring it low to halt it. Because of that, I'll send the most significant bit of the opcode through an inverter to pin 10 of the counter. Then I'll just add the remaining 5 inverters down here since I'll be using a 7404 hex inverter IC, which contains 6 inverters. Now, we really should have one more instruction before we start testing this out. Instead of halting the counter, why don't we create an instruction that allows it to continue counting without doing anything else? I'll call this instruction NOOP, short for no operation, and it'll be the same as the halt instruction except that the most significant bit will be a 0. So, why would we want to have a NOOP instruction? No-ops can be used for a variety of reasons. For example, we may want to use it for timing purposes, to wait for something to complete. We can also use it to help align instructions to certain addresses. Or maybe we want to use it as a placeholder for another instruction. This can be used for debugging. It's kind of like a way to comment out part of your code without moving other instructions around. We really don't need to do anything else to the circuit to implement this no-op instruction, so we're good so far. But there are some things that we need to do to get this counter to count. We need to pull pin 9 high, which is used as a load enable pin. If that pin goes low, then we load in the address from the operand. Pin 7 also needs to be pulled high to get the counter to count. And pin 1 is the master reset. We can reset the counter by pulling this pin low, so we need it high to count. Finally, we need a clock signal to go to pin 2. So now, let's write a short program to count from 0 to 5, then stop. I'll just use 5 no-op instructions, then a halt. Let's put this code into the flash chip. Since DigitalWorks uses zeros for an empty flash chip, we don't need to add any no-ops, since the zeros will act as no-ops. I'll just add in a halt, which is 80 in hexadecimal, to address 5. Actually, the operand could be anything, but I'll just make it a 0. Now, if we run this, we should execute up to address 5, then halt. And that runs just fine. Now let's breadboard this up, but before I do that, I'll just program this flash chip to match the program we had in DigitalWorks. I'll first ID the flash chip, then add 5 no-ops, which are 00 hex, then the halt, which is 80 hex. Now let's go back to address 0 and dump out 16 bytes to make sure this looks correct. And it does. Okay, I'll just place the flash chip right here. Oh, and just a heads up, this will be a fairly sloppy build since I'm not a very neat plague. But you probably knew that, and this is just a temporary CPU design anyway. I'll try to be neater when I build larger CPUs. Now, notice that there are 2 breadboards. The upper breadboard with the flash chip is not part of the CPU. The CPU will be contained on the lower breadboard for now. And I'll connect power and ground up to the flash chip. Then I'll connect all the address lines on the lower side of this chip to ground, except for address lines 0 through 3. Those will be used by the instruction pointer. I'll connect the right enable line to VCC to disable it. Then I'll ground out more address lines. I'll ground the output enable line to enable the output, then ground the next address line. Then finally the chip enable will be grounded to enable this flash chip. I'll add a 0.1 mic bypass cap from power to ground. Then let's put the 161 counter down here, since it is part of the CPU, and I'll put the hex inverter next to it. I'll place 0.1 mic bypass caps on the power inputs to these chips, and add power and ground. I'll just terminate the unused inputs to the inverter. Then I'll connect the load pin of the counter to VCC, along with pin 7 to enable counting. I'll just place a reset switch next to the counter so we have a way to reset the counter. I'll place a 100K pull-up resistor on the side of the switch that will connect to the counter reset pin. And for those that don't know, the 2 pins on the right side of the switch are both connected to one side of the switch, and the 2 pins on the left side are both connected together internally on the other side of the switch. I'll connect the other side of the switch to ground so we bring the reset pin of the counter low when pressing the switch. Then I'll just connect the resistor side of the switch to the reset pin of the counter. I'll connect the outputs of the counter to the lower 4 address lines of the flash chip. Address 0, 1, 2, and 3. I'll connect the output of an inverter to pin 10 of the counter. This will be used for halting the CPU. I'll bring the most significant bit of the flash chip data to the input of the inverter. I'll connect the lower nibble of the data lines to the loading inputs of the counter. Data lines 0, 1, 2, and 3. That should be all for the CPU design so far. Now I'll add in a 74541 buffer on this upper breadboard so we can easily drive some LEDs. I'll give it a bypass cap, along with power and ground. I'll ground both output enable pins to enable the buffer. And I'll send the 4 address lines through the buffer. Then terminate the unused inputs. Let's put an LED bar graph over here and connect up an array of 470 ohm resistors. Then I'll connect up the outputs of the buffers to the rightmost 4 LEDs. Remember the clock source that I made in some past videos? I'll just place that down here. And I need to get the clock output way over to the counter chip, so I'll just add some wires to do that. Very sloppy, but we'll get it to work. Okay, I'll use this here bus strip for connecting all the power and grounds together. Not the best method, but it should work for now. I'll just connect the power and ground from my power supply to the center of this bus. Then maybe add in a bulk 10 mic capacitor for good measure. Okay, let's give this a whirl. And it does halt at address 5. Beautiful! Now, before we continue, I want to make this a little easier to visualize. I'm going to replace the 74161 counter IC with a macro that I created. Now, don't worry, the IC didn't go anywhere, other than it's been placed inside this macro. We can see which pins on the macro that each IC pin connects to. And if we back out, the pins on this macro are defined in a counterclockwise direction from pin 1 right here to pin 12 up here. So now, the most significant bit is pretty much spoken for with this CPU, and that leaves us with 3 more bits for additional CPU instructions. I'm actually going to send those remaining 3 bits into a 3 to 8 line decoder, and I'll choose the 74238, which has non-inverting outputs. Notice that I had to juggle these lines around a bit, since the pins on the 238 are flipped from what is on the ROM chip. Now, the 238 IC has 3 enable pins on it. 2 need to be low to enable the chip on pins 4 and 5, and 1 needs to be high on pin 6. I'm going to send the most significant bit of the opcode to one of the low enable pins, pin 4. What that is going to do is disable the 238 when we encounter a halt instruction. This really isn't needed if the halt instruction is written properly with zeros in the 3 least significant opcode bits, but it just adds some extra protection from rogue instructions. I'll then connect a reset switch to both the reset pin of the 161 counter IC and the high enable pin of the 238 decoder. The reset switch needs to be high when it is not pressed, and it should generate a low when it is pressed. Therefore, pressing the reset switch will drive the reset line low and reset the entire CPU. I'll connect the final enable pin of the 238 to the clock line. If you'll recall from my part 2 video on designing the Plague Mark I CPU, I used a technique called strobing, and by connecting the clock line to an enable pin of the 238, we'll be using the strobing feature in the Plague Mark II. Now, with the 238 decoder connected up, we've gained some additional possibilities for CPU instructions. Let's now create one more instruction. This will be a simple one. I'll choose the second bit in the opcode for this one. No particular reason, just sounds good. And I'm using my creativity here. What I am going to create is an out instruction, very much like the Plague Mark I, but this will only output 1 bit, at least for now. This may not make much sense, but stay with me here. It'll be changed up a bit later on. Since this instruction only outputs 1 bit, we don't need the operand nibble, so I'll mark it with more X's. Now, the hexadecimal value of this opcode, or even the decimal value for that matter, is 2. Since the outputs of the 238 decoder start with a value of 0, 2 will be the third output pin, which will be on pin 13 of the IC. I'll just connect that to an LED for now. Now, so far, this CPU supports 3 instructions: no op, halt, and out. Beautiful. Let's give this a quick test. I'll use the same code from before, but change 2 of the no-ops to out instructions, which is 20 hex. Now, when we run this, we should see the LED light up twice, assuming that we're using a slow enough clock speed to see it. And sure enough, we get 2 flashes of the LED. Great, let's breadboard this up and make sure everything still works. First, I'm going to take out the flash chip to reprogram it. I'll ID the flash chip and erase it. Then I'll program it with alternating no-ops and outs, which are 00 hex and 20 hex. Then finally a halt, which is 80 hex. And let's dump it out. Looks good. I'll put the flash chip back in the breadboard. Let's just add the 238 decoder chip next to the hex inverter and our 0.1 mic bypass cap. Then power and ground. I'll just connect our opcode bits to the address in pins of the decoder. Data lines 4, 5, and 6. Then I'll send data line 7 to one of the active low enable pins of the decoder. I'll send the strobing clock signal to the other active low enable pin of the decoder. And the active high enable pin will connect to the reset line. Then I'll send output number 2 to an LED through a buffer. Remember, the output pins start at number 0. And let's give this a go. I'll reset the CPU. Notice the output LED did blink twice. Let's see that again. 1, 2, and we stop at address 5. Fantastic! Now, again, like I did with the 161 counter IC, I'm going to add the 74238 into a macro to help us visualize how it's connected. And we can go inside to see the pins it's connected to. And on the outside, the pins are numbered from 1 to 14, with pin 1 being here, and going counterclockwise, we get pin 14 up here. Beautiful. Now, as I've mentioned in the past, the Plague Mark II will be able to perform some simple math, and what I wanted to do is to add numbers together. Since the operands in this CPU are 4 bits, I want to add 2 4-bit integers together. So let's talk a little about how to create an adder. I'll first create an adder to add 2 single binary digits, A and B. So I want the inputs to this adder to be A and B. If A and B are both 0, then the sum is obviously 0. If either input is 1, then the sum is 1. If both A and B are 1, then the sum is 2, which is 1, 0 in binary. Since this last result is 2 digits, I'll make all the results 2 digits by adding a 0 in front of them. These will be the outputs, with the sum being the rightmost digit, and the left digit will be a carry-out bit. Now, if we look at the sum, we'll notice that it is only 1 when A and B are opposite values, which is the very definition of an exclusive OR operation. So, we can send A and B into an exclusive OR gate to get the sum. Now, the carry-out bit is only a 1 when both A and B are 1. This looks a lot like an AND operation, so let's send A and B into an AND gate to get the carry bit. This is called a half adder. We need more than this, though, because we need to add 2 4-bit integers, not just 2 1-bit integers. The next 2 bits that we add together will require the carry-out bit from the first 2 bits that were added. So we need to add 2 bits, A and B, and a carry bit, which we'll call the carry-in bit. This will make what we call a full adder. So we have 3 inputs, the carry-in, A, and B. And of course, we still have two outputs, carry out and the sum. Okay, let's write out all the combinations of inputs. There will be 8 of them. Now, when all the inputs are 0, the output will be 0. If any of the inputs is exclusively 1, then the output will be 1. If 2 and only 2 inputs are 1, then the output will be 2, which is 1, 0. And finally, if all 3 inputs are 1, then the output will be 3, which is 1, 1 in binary. Now, to get the sum is fairly easy. We know that exclusive ORing 2 bits sums those 2 bits. So we can send A and B into an exclusive OR gate. Then we can add the carry-in bit to that result by exclusive ORing that output to the carry-in bit. So I'll exclusive OR A and B together. Then exclusive OR that column to Cin. And we can see that this sum equals the sum from this previous table. Now we need to get the carry out. Let's take the AND gate from the half adder and apply A and B to that. And transfer this column to a new table. Then let's take A exclusive OR B from this table and AND it to the carry in, like this. Let's transfer that result to this table. Now let's OR these 2 columns together. And notice that this carry out column is the same as the carry out column from this table. So let's finish building the circuit. We'll AND together the output from A exclusive OR B to the carry in. Next, I'll OR together the 2 outputs from the AND gates. And that will be our carry out bit. This is the complete full adder. Now, to add 2 4-bit integers together, we can use 1 half adder and 3 full adders. But we don't actually need the half adder. We could just use 4 full adders, like this, where we carry over the carry bits and just ground the first carry in bit. Now we can add any 2 4-bit integers together, such as 4 and 5, which is 9, or 12 and 5, which is 17, etc. And while we could wire all these gates up and it would work, let's not do that. This would take a lot of logic gates to create a simple 4-bit adder, but we're in luck, because there are already some 74 series ICs that can add numbers together. Let's look at the 74283 4-bit binary adder. This IC will take in 2 4-bit inputs along with a carry input bit and provide the sum of those inputs on its output pins along with the carry output bit. Fantastic! Let's use it! So I will create another instruction to add the operand to another number, to be determined later. I'll just choose the least significant bit of the opcode. I mean, why not? It's there for us to use. Then, the operand will contain an immediate value to be added to some other mystery value. So, I'll use the letter I to indicate an immediate value. Let's place the 283 adder right here, and I'll connect up the operand from the flash ROM to input B of the adder. For now, I'll just place some switches on input A of the adder to allow us to choose this mystery value that we are adding to. There won't be a carry input to this operation, so I'll just ground the carry input pin, which is pin 7. Then, for now, I'll just connect up the outputs to 4 LEDs, and connect the carry output bit to a 5th LED. Now, to understand this next test, you'll need to be a little familiar with binary numbers, so be sure to brush up on those if you're not comfortable with binary. So, I'm going to write some code to add, let's say, 3 to whatever value the switches are set to. Let's start with a no-op, then add 3, and finally a halt. A no-op is 00 hex, and add 3 is 13 hex. Then we have 80 hex for halt. I'll set the switches to a value of 2, so that means we should get 3 plus 2, which is 5, for the result. Let's run it. And notice that we did get 5, but it disappeared quickly since we're not storing that value. Also, when the value of 5 was not showing up in the sum LEDs, the sum showed a value of 2, which is what the switches are set to, and they're being added to 0 during the no-op and halt instructions. Let's reset it to show that again. And let's change the switches to a value of 7, so we should get 10. And we do. So the problem here is that the sum value is not stored. Let's fix that. I'm going to add in a register that can store the result. We could call this an accumulator, but I'm going to call it Register A, since the final version of the Plague Mark II will have more than one register. Before we add a register, let's clean this up a bit by placing the 283 adder IC into a macro like this. Here are the innards of the macro. And again, the pinout starts with pin 1 here, and going counterclockwise we have pin 14 here. For the register, I'm going to use a 74-273 octo D flip-flop with reset, so we can zero this register out before using it. So I'll just disconnect the LEDs and add in the 273 register right here. I'll connect the output of the adder to the first 4 inputs of the register IC. And I'll connect the first 4 outputs of the register IC to the register LEDs. Then I'll send the carry out bit through the 5th D flip-flop of the register IC. Now, we need to be able to latch in the sum value when the add instruction is executed. Since the add instruction has an opcode of 1, I'll connect bit 1 of the decoder output to the clock input of the register IC. And finally, we need to make sure the register is cleared to 0 whenever a reset occurs. So, I'll connect the reset line to the master reset of the register IC. Now we should be ready to see the correct sum retained in register A whenever the add instruction is executed. Let's execute the same code we had last time. We'll first try it with the switches set to 2, so we should get a value of 5. And perfect! Let's try 7 and see if we get 10. And yes, it's 10. Now let's test the carry bit by changing the switches to 15. And we get 18 as expected. Perfect! Let's place this register into a macro. And here's the inside. Going back we have pin 1 here, and going counterclockwise we have pin 18 here. Now this looks a little neater and easier to see how everything is connected. Let's breadboard this version up and make sure the same tests pass. And again, I'll first reprogram the flash chip. So I'll erase it, then program a no-op, 00 hex, then add 3, which is 13 hex, and finally a halt, 80 hex. Let's dump this. Perfect. Okay, let's put the 283 adder chip here, and the 273 register chip next to it. And we'll get the 0.1 mic bypass caps on the board. Followed by power and ground for each chip. I'll connect the lower nibble of the flash chip data lines to input B of the adder, data lines 0, 1, 2, and 3. Then I'll send the sum from the adder to the register chip, bits 0, 1, 2, and 3. I'll ground the carry-in bit since we won't be using that. And I'll send the carry-out bit to the register. Then I'll connect the master reset of the register to the reset line. let's connect the clock input of the register to output number 1 of the decoder chip. Then I'll just terminate the unused inputs on the register to VCC. I'm going to disconnect the output LED from the buffer to help make room for the register output. And since we have 5 bits of output coming from the register, I'll just disconnect the most significant bit of the address from the LEDs, since I only have 8 buffers to drive the LEDs. I'll move the 3 address lines to the upper most significant LEDs, so I can use the lower 5 LEDs for the register output. And of course, the 2 leftmost LEDs will be unused, since the LED bar has 10 LEDs and I'm only using 8 of them. And I'll disconnect 5 of the inputs to the LED buffer so we can use them for the register value. Then I'll connect bits 0, 1, 2, and 3 of the register to the LED buffer. I'll just connect the outputs of the buffer to the LEDs. Okay, let's place the switches off to the side over here, and I'll just use little tactile switches. And let's bring ground and power to this new breadboard. I'll pull the outputs of these switches to ground with 100K resistors. Then I'll tie the inputs of these switches to VCC. And finally, I'll connect the outputs of these switches to input A of the adder IC. Bits 0, 1, 2, and 3. Now, if you've been paying attention, you've probably noticed that I made a mistake on the order of the register bits to the LEDs. I've got the lower 4 bits backwards, so I'm just reversing them. Even us plagues make mistakes. So, before I run this little program, I'm just going to bring a copy of the upper 5 LEDs up here, and then cover up the 5 LEDs on the lower bar graph. This will make it much easier to see the address and register values. Okay, let's power it up and give it a shot. First, I'll reset it. Then I'll input a 2 to the adder and run it. And it gives 5, which is 2 plus 3 for the result. Let's try inputting a 7. And I get 10. I'll try pressing all the switches. We should get 18. And we do. Awesome! Okay, now there is going to be a small problem with this setup. Let's try placing the add instruction as the first instruction followed by a halt. Didn't quite work, did it? Let's try resetting it. Nope, that didn't work either. Maybe it's the simulator, you might think. So let's try it on the breadboard. I'll quickly reprogram the flash chip to remove the no-op. By adding 1, 3, and 8, 0. Then replace it. And power it up. Well, now we get 3 displaying right away after resetting it. But if I input 2, then it should display 5 after running it. And no dice. What's going on? What's the problem here? Do we need to have a no-op as our first instruction? Well, that would be pretty sad, wouldn't it? Actually, we don't need a no-op. We just need to understand why this isn't working. And with that said, we'll pick up where we left off in the next video. In the meantime, see if you can figure out what's going on. And I'll provide my simple solution next time, right here on Dr. Plague.